Hello, today we're going to go over this problem that has to do with module 4.2.2, and pretty much in this problem we're following the procedure that is explained there. So if at any point you have questions of why do we follow the procedure, please go and read this section in our textbook because it does have all the explanations. And in this model, it's a nice combination of the idea of eigenvectors and eigenvalues and Markov chains. So what we do is we start with a biologist that is doing an experiment with bacterial population. There are infected population and non-infected or infection-free. And the population is 50.7 of infected bacteria versus 14.5 infection-free bacteria, and our units are in million of bacteria. So according to the theory, 90% of the infected bacteria are going to keep infected, the remaining will recover, and out of the healthy bacteria, 40% will get infected, and the remaining 60% are going to recover. So that this problem already tells you how to set it up with the transition matrix, so that is given. And in this problem, they also do the work of computing the eigenvalues and eigenvectors, the corresponding ones. And once that you have all of this information, the question is telling you, okay, consider this as a problem with an emphasis in the Markov chain. Use that technique to predict the population of infected bacteria after a week. And because things were in terms of hours, after a week is a lot of hours, that means that we're really looking for the steady state, and it says that explicitly. So I'm going to go over the procedure, and these are our options, so you're going to see which one among these options is the correct solution. Okay, so we have our initial population now in a vector. So my first row corresponds to the number of infected, and the second one to the number of non-infected. And because this is my initial population, we usually denote that by x naught. So at time 0. And I have my transition matrix. This we don't get to use it, and what the information that I use about the transition matrix is that it has these eigenvalues and with corresponding eigenvector. And we usually denote those by v's, but if you look again at 4.2.2, we want to just call them u1 and u2. Okay, so the first thing that we want to do is find a way of writing x naught in terms of u1 and u2. So you want to find two constants, we're going to call them c1 and c2, such that I will have x naught equals c1 times u1 plus c2 times u2. And to do that, we just set it up as it is. So x naught is 50.7, 14.5. That has to be equal to a constant c1 times my vector u1, so 1, negative 1, plus a constant c2 times the vector 0.6, 0.1. This doesn't look like a point, but there's a 0.1. So that means that because these are unknowns, we can convert those into variables, and out of this I will build a system of equations, right? So the system of equations is c1 plus 0.6, c2 equals 50.7, and negative c1 plus 0.1 c2 equals 14.5. And out of this, what we can do is you can solve this system of equations. At this point, you can use whatever you want, but because I like our class and the material that we have, I'm going to just reduce my augmented matrix. My augmented matrix is just 1, negative 1, 0.6, 0.1, and 50.7, and 14.1. Sorry, 0.5. Okay, so there's not much that we need to do, and that's great. So using this one, I'm going to make this 0, so that means that I'm going to just add these two, and that means that my operation is going to be row 1 plus row 2, and that gives me 1, 0.6, 50.7, 0, 0.7, and 65.2. And now I need to turn this into a 1, so I'm going to do 1 over 0.7 row 2, that goes to row 2, and that's going to give me 0, not 0, 1.6, 50.7, 0, 1, and 93.14, 29. Then finally, I'm going to do that here. What we're going to do is we are going to do, using this 1, I'm going to make this 1 a 0, so that means that I'm going to do minus 0.6 row 2 plus row 1, and that goes to row 1. And when I do that, I get my matrix 1, 0, 0, 1, and the numbers that I'm going to get in the augmented part are negative 5.1857 and 93.1429. Okay, so this tells me that x naught equals my constant C1. So remember, this was C1 and this was C2. So my constant C1, which is negative 5.1857 times U1 plus the constant C2, which is 93.1429 times my vector U2. Okay, so we have now the constants or scalars that we have multiplying our eigenvectors, and that means that, and again this is according to our theory, xk is going to be this constant one minus 5.1857 times my first eigenvalue lambda 1 to the k times u1 plus 93.1429 times the second eigenvalue to the k times u2. So when we take the limit, well, actually let me substitute. So this is negative 5.1857 times 0.3 to the k times the vector, or multiplying the vector 1, negative 1, plus 93.1429 times 1 to the k times the vector 0.6, 0.1. So this is my xk. And now if I want to figure out what is the steady state, for the steady state, That means that you want to take the limit when k goes to infinity for xk. And I'm going to just use what we have here, the limit when k goes to infinity of this thing. Of course, I have to do the limit when k goes to infinity for all of these things. But let's see what happens. 0.03, it's a number that is smaller than 1. When you multiply times itself, this is going to go to 0. So it's going to basically, this whole part is going to cancel out. And the remaining part, because 1 to the k is always 1, this is going to stay here. So in the limit, this is going to give me, this other color, 93.1429 times 0.6, 0.1. So this gives me the steady states. And then when I go back, I see that the question was asking for the number of infected, and remember the number of infected is this one, my first entry. So the number of infected is going to be just the multiplication of 93.1429 times 0.6. And that gives me 55.885. When I round it, this rounds to 55.9 million. Remember that the units were million of bacteria. And that means that the answer is option A. And that's it. That's how we arrive to the answer.